X denote the loss amount sustained by an insurance company's policyholder. Let Z denote the portion of X that the insurance company will have to pay. An actuary determines that X and Z are independent. With respective density and probability functions given below. Okay. So calculate the variance of insurance company's claim payment ZX. So to calculate the variance of ZX, we will find expected value of ZX and expected value of ZX whole square, and then use our normal formula for variance. Okay. So Z and X are independent. So expected value of Z, or expected value of Zx will be expected value of Z times expected value of Ex. And therefore, we do need the expected values of these individual variables. So now you can see that X is an exponential variable with mean 8. Remember, the PDF of an exponential is 1 over mean e to the negative x over mean. So x is exponential with mean 8. And the variance of an exponential variable is the square of the mean. So the variance of x is 64. So now we will need, since remember, we want variance of zx, so we will need expected value of zx and expected value of zx whole square. And to do that, we will need the expected value of x squared. So right now we have variance of x, which is 64, and the expected value of x is 8. So we use our typical formula. The variance of x is e of x squared minus ex whole square. So variance is 64. E of x squared we are trying to find from this formula, minus 8 squared. And 8 squared is 64, and this one gets added over here. So e of x squared comes out to be 128. So e of z is a discrete variable like this. So you know that for such variable, the expected value will be the value of z times the corresponding probability. So basically it's summation of z, f of z. So it'd be 1 times the probability plus 0 times the probability of 0. So 1 times 0.45 plus 0 times 0.55 equals 0.45. And similarly, of z squared will be, now it's the same thing, but instead of the z values here, which were 1 and 0, you do the z square values, 1 square and 0 square, and the probabilities are still the same, 0.45 and 0.55. So this also comes out to be 0.45. So now we have all the bits and pieces that we need. Z and again, as we said before, X and Z are independent. Therefore, their product, the expected value of their product splits up into the individual expected value products. So E of ZX equals E of Z, E of X. Remember, this applies only if Z and X are independent. The distribution over sum is always true, whether they're independent or not, but the distribution over product for expected values is only true if they are independent. So E of Z is 0.45, and E of X was the mean of the exponential, which is X, which is 8. So that's 3.6. And we also need E of ZX whole square. So distribute the square, that's E Z square X square. And now again, since Z and X are independent, so Z square and X square are also independent. Therefore, we can split up the E of Z square X square into E of Z square times E of X square. E of Z square is 0.45. E of X squared was calculated above, 128. And that's 57.6. So now we are on to our final step. The variance of Zx is equal to E of Zx whole squared minus E of Zx whole squared. So equals 57.6 was the expected value of Zx whole squared. And the expected value of Zx was 3.6, and you whole squared that one. 44.64. This rounds to choice E.